Okay, so this is a set of slides that we showed quite recently on ATM seminar this year. This was joint work with, well, NASA. So NASA at some point, NASA employees, they went to work in Crown Consulting. I'm not sure about the full story, but there was something when the government was shut down for some time in the US, so NASA employees couldn't get their funding. Anyway, so Crown is really NASA, and that's the work that we did with NASA and supported by some of the local authorities, but also by some of these projects that I mentioned that also are part of UAM Explained, Airborne Chorus X UAM. So Chorus X UAM is particularly, I mentioned it again, it's a particularly interesting project. It does the concept of operations for urban air mobility. So Chorus first was just for UTM, and now we are trying to extend it to also cover the urban air mobility. So speaking of risks, we are flying with these expensive planes for quite some time. And we know that losing the whole losing a plane is a catastrophe in itself. There are people on board, they cost a lot. All in all, there is a lot of risk that the first part is the people flying with the aircraft that they have. Economical risk and also, of course, risk to people's life. On the other hand, if you think about UTM, well, these unmanned drones, first of all, they're unmanned. So there is really no big deal if one of them is lost, first of all, in terms of people's life, but also in terms of money. I mean, okay, they may cost maybe €1,000, and maybe there is a payload, I don't know, pizza or whatever, which also costs something. But all in all, it's not such a big deal if a drone falls from the sky for the drone. What is, or maybe a big deal, is the harm to the people on the ground, in particular because they are really uninvolved. So people in the aircraft, well, I mean, at least they know they're flying the aircraft. Well, we can discuss whether there is a moral dilemma in the people taking the airplane, understanding the risks and so on, whether we have to understand the risks. But people who are on the ground, they are really uninvolved in the operation. It's not their delivery, it's not their drone and so on. They just happen to be under the drone. And we want to minimize or at least understand the impact of the drone operations for people on the ground. And surprise, surprise, it's important to take the population distribution into account. It has taken some time to understand what is important and what is super important when we're talking about UAS or drone operations. So if we look at the first concept of operations that was developed by NASA like 5 years ago, they were thinking really about a centralized system that have awareness of, well, pretty much everything. You have to know about the airspace, of course, and about people, and even about animals on the ground, and so on and so forth. And of course, you could have made a lot of fun. You know, what size animals are we talking about? And I do make this fun in the other set of slides. But all in all, this was not too bad. We had to start from something. So NASA started from the first ConOps, and they had some understanding of how the operations and, more importantly, how UTM should look like. It's similar to regulations. I mean, regulations are not ideal, but it's much better than having no regulations at all. Similar to the ConOps. Okay, NASA ConOps now had questions, but now you could have questions to it, but I mean, it was something. And then in the few years afterwards, already in the regulations 947, which we are also studying, it says that, yeah, I mean, we can, in principle, overfly uninvolved people. They shouldn't fly over assemblies of people. And of course, in the regulations, there is a definition of assembly of people. People are in an assembly if they are so tightly packed that they cannot move if they want to. Of course, that was in 2019, and then Corona came in, and people in general should not be so close to one another that they wouldn't be able to move. Anyway, there is something where some understanding of flying over people is coming. And then again, the story continues. There are lots and lots of papers and works that look at the risks posed to people on the ground, and in particular, the work that I'm presenting right now is also fits into this line of work. Now, before we go into UTM, it's interesting that just in February this year, February 2021, as we were actually working on the ground risk of drone operations, they came in the news that there were actually two events, one in the US, I think it was near Denver, and one in the Netherlands, when debris from aircraft were falling down on the ground. I don't know, maybe that's just Google understanding that I work on something started showing me these news. Or maybe indeed there was not the case before, but somehow these days we speak more and more about integration of UTM and ATM. In particular, we speak about UTM inspired ATM. So we want to learn from UTM and take the lessons into ATM. ATM is air traffic management, the conventional aircraft management. And of course, in the regulations lecture, again, we looked at the regulation 665, which I think is not in the final stage yet, which was saying that, yeah, U-space may be shared also by other aircraft other than drones. In some sense, they would have to become drones to enter the U-space, have electronic conspicuity and all that, and it's not clear yet how exactly it will be done. But still, I mean, this question of things falling from the sky and posing risk to people on the ground may also be relevant to ATM, not only in UTM. But UTM at least brings in some novelty. And well, here is how the risk assessment looked before SORA. And if you see in the blank screen, then this is what I meant. I mean, we were in complete darkness. We didn't know how to do the risk assessment for drone operations. I mean, of course, risk assessment for aircraft operations has been there for more or less as long as the aircraft are flying. And then SORA came in, and with all the drawbacks and ambiguities about which I will speak, SORA really shed a lot of light on how to do risk assessment. It's a procedure. After all, you can do it. And SORA is qualitative by design. I mean, it's not something that can be really executed by a computer. I mean, there are many places where you can see that. You can, of course, see SORA yourself, and you at least see the video about SORA and look at the regulations. So this European Cockpit Association had this particular opinion saying that, well, it's not quantitative. Quantitative would be something that you could really want to risk assessment could execute by a computer. And in SORA, there are quite a few places, and I will be showing some of them, where you have to have an opinion, have subjective, some kind of judgment. Anyway, SORA is qualitative, which may be a good thing, but I'm not discussing that now. But if you want to achieve certain level of safety, or as they have been speaking about, ELOS, equivalent or equal level of safety, equal to that of the manned aviation, we have to do quantitative risk assessment, right? We have to measure what the risk is. And when we're speaking about equivalent level of safety, we should ask ourselves, well, how do you measure the level of safety? What is the level of safety? Sometimes they call it TLS, target level of safety, TLS. How is it measured, and how can we ensure that we have the equivalent level of safety in the UTM as we have in the conventional ATM? And well, the answer is kind of there. The level of safety is measured in the fatality rate. So how many people in expectation may die per flight hour? And you can find this in quite a few documents. In the first version of SORA, it says very specifically that, yes, the number of fatal injuries, so fatalities, to third parties on the ground per flight hour, expected fatality rate, is the best parameter that embody the equivalence of risk. The second version of SORA, well, I mean, it also states similar things. I mean, it measures fatalities, number of deaths within particular time interval. I guess it's not just the time interval, it's really, of course, per flying hours. Not really measuring it just per year, but per hours of flight. So I think that second SORA is less specific about it. I will show a few other examples where I think somehow second SORA is, well, in my opinion, I mean, it's to my taste, possibly even not as good as SORA number 1. Maybe that's why I was uploading so much when I saw SORA for the first time, and then I looked at the second SORA, and it was, well, there are some places which less clear. But anyway, SORA number 2 is there now, and it still stays the same thing. As regards the risk, it's the expected fatality rate. And then there is also the Arctic Science RPAS, remotely piloted aircraft systems handbook, written by quite a few people from Norway. I think there are some Swedish contributors and so on. It has also been in some classical work. Anyway, in many places, you can find that this expected fatality rate is the measure of the level of safety, and it's measured in the number of fatalities per flight hour. So normally it's 1 fatality per million flight hours, so this should be like 10 × -6 fatalities per hour. But I know that this number has also been challenged. They've been looking at the real number of fatalities. It was something around that, around 1 fatality per million flight hours, but maybe not exactly. Anyway, there is some target level of safety, and the level of safety is measured in the number of fatalities per flight hour. And here is one simple example, and I would encourage you to do the arithmetic, and maybe if you can get the answer, you can put it in, let's say, in chat. Let's say that there is a drone, and it fails from time to time. So from time to time, the drone does fall off the sky. And every time it happens, every time there is a failure, 10 fatalities happen. So 10 people are killed by this drone. And the drone fails approximately once in every 10,000 hours. Okay, so there is a failure, then about 10,000 hours, another failure, and so on. So if you look at the time axis. Okay, so every 10,000 hours, there is a failure, and 10 people are killed every time there is a failure. So what is the fatality rate, expected fatality rate? How many fatalities per hour do we have? So, well, the simple arithmetic that you hopefully can do is that, well, if 10 people are killed within 10,000 hours, then the expected fatality rate is 1 person in 1,000 hours. Or more importantly, of course, not this example, but to understand this formula, that the expected fatality rate is the number of fatalities per 1 failure divided by the time between failures. So the prerequisites for this class stated that you have to have some basic notions of mathematics. Well, here we go. I hope you can do the division. So the fatality rate is the number of fatalities divided by the time between the failures. And of course, what can happen is that the number of exposed people during a failure is very large. So I don't know, the drone can fall anywhere within 100 by 100 meters square, and there could be 100 people in that square, but not necessarily every one of them dies. So the drone doesn't really sweep this whole impact area. So maybe there is certain probability of fatality if you're exposed to the drone failure. Maybe a person dies only with probability 10%, 1/10. And then the expected number of fatalities per failure is only 10. So 100 people are exposed, but only a 10th fraction of them dies. So the number of fatalities is the number of exposed people times this probability. So here is the formula. expected number of fatalities is the number of exposed people times the probability that the person dies if the person is exposed. And we have a formula for the expected fatality rate, number of fatalities divided by how often they happen. And we substitute this number of fatalities formula here for the number of fatalities. And here we have the formula for the expected fatality rate as a function of the number of exposed people, the probability of people being sheltered, if you want, or non-sheltered rather, and dying if they are exposed, and of course divided by how often the fatalities, the failures happen. Okay, so I'll put it here in the title of the slide. This is the expected fatality rate. Okay, we'll work with this formula through a few other slides. Okay, I mean, this formula is no rocket science, no drone science. It's more or less understandable that the more people are exposed, the higher the expected fatality rate, the higher the probability that an exposed person dies, the higher the fatality rate is. And of course, the less frequent the failures are, the smaller the fatality rate is. And you can see formula like this, or exactly this formula, in quite a few places. Again, in SORA 1, there was this figure, which I think, well, it has the same 3 terms, and again, explains more or less the same formula. It does speak in terms of likelihoods, and well, I'm not sure exactly what likelihood is, but anyway, so likelihood of fatal injuries, so essentially fatality rate, is the likelihood of having the operation out of control. So that's the failure. And then there is this likelihood of a person being struck if the operation is out of control. So that's kind of the number of exposed people. So if the UA, unmanned vehicle, the drone, is out of control, if there is a failure, then how many people are hit. And finally, this probability, as they say, likelihood, that if the person is struck, the person dies. So again, 3 same or similar terms. And for some reason, it was, yeah, this particular figure was gone from SORA to 0, which is the current SORA. I'm not sure why. Anyway, that's my one disappointment with SORA to 0. But still, the formula is still there, whether it is in SORA or it is not. Now, when we start dissecting this formula and looking at the different terms in it and thinking, when you are planning a route for the drone, what exactly, which terms in this formula are you influencing? So the time between failures, I mean, it's more or less set or decided, or it's more or less up to the manufacturer, how reliable the drone is, how well it is certified, and so on and so forth. As a route planner, okay, I mean, maybe it depends on the weather. If the weather is inclement, hazardous, then the drone has higher probability of failing, but still it's kind of outside of immediate route planning. So you have certain weather, or maybe assume that the weather is good, clear weather, no wind or light wind, and so on. And then again, as a route planner, you don't influence how often the drone fails. Then this probability. Recall that this probability is the probability of a person being killed if the person is exposed. And again, it doesn't really depend on the route the drone takes. I mean, or on the route planner. So people may be in the shelter, and if they are, then the probability is low. The drone may have or have no parachute. There may be many other mitigations. But again, if you have a given drone and you know where people are, then you don't really influence the probability of a person being killed if the person is exposed. You do influence it indirectly via the speed and hence the energy of the drone. But again, if you know the speed with which the drone wants to fly, then well, you don't really influence this probability. What is influenced by your route is the number of exposed people. So depending on where you fly, what is the population density that you overfly, you change the number of exposed people, and hence the expected fatality rate, hence the risk. And what we will look at next is how you can estimate the number of exposed people. So we'll look at how it was done before, and then what we are doing in our latest and greatest work. So in several earlier works, the number of exposed people was estimated in a very simple way. It's the exposed area times the population density. So what is the exposed area? It's something that's sometimes called the lethal debris area. It's more or less how far the debris from drone can reach if the drone fails at a certain point. So the drone fails somewhere here in the center, and well, there is certain radius r within which the debris may fall. I mean, it may be a circle, it may be a square. You can model it in different ways. You can also do fine-tuned modeling. But if r is the distance that can be reached by the debris, then, well, more or less, the exposed area is proportional to r squared. What the coefficient of proportionality, whether it's pi, if it's the area is a circle, or whether it's 4, if the area is square, that's a different story. That doesn't matter too much. But yes, the exposed area is proportional to r squared, where r is the distance reached by the lethal debris, the debris that can kill a person. Okay, so that was the exposed area. And then you multiply that by the population density. So there is certain population density in this area. And to know the number of people exposed, well, we multiply the exposed area by the population density. And in previous work, the population density was assumed constant, meaning that the number of exposed people is also constant, and the expected fatality rate is constant. So there was nothing about path planning. So that work really looked at, different kinds of operational environments. If you're in densely populated area versus thinly populated area, what would be your EFR? What will be the number of exposed people, and so on and so forth. And what we've been doing is working with arbitrary density, arbitrary population density for the drone operations. And this is what I will explain in the remainder of this lecture. But first, I want to point at the GUI. It's also linked from the web page. So this is essentially the route planning tool. You can go to this webpage and click the route points yourself. Use the right mouse buttons. You can, that's North Shopping, by the way. And the heat map underneath is the population density. And you can change this radius, or the distance of the lethal debris. So how thick the path is, how many people are affected. And as you do it, you see quite a few KPIs that are shown. Well, how many people are exposed, and so on and so forth, affected area, and other things. And moreover, you can drag, your route, you can drag the points and see how the exposed population and other parameters change along this path. And of course, if you go on a direct path, then you're exposing a lot of population because you may be flying through highly populated areas. But yes, if you go around, I don't know if that was the most optimal way or any good way to go around, then you see that the exposed population is much less, but of course the route becomes much longer. So you can play around yourself with our tool. And now returning to its description, essentially what our tool outputs and what we take care about is that there can be several paths between the same origin destination point. So here on the picture in the lower corner, while the drone may fly from A to B directly, but maybe there is a kindergarten and people gathering on both sides of the route. So this red route would have very high risk. It would be very short, but would have very high risk. So it's represented by this point in the axis with length and risk. Short route, but high risk. There is this green route, which flies around, maybe like there is a parking lot, and It's longer, so its length is a bit longer, but it has lower risk. And last but not least, there is maybe this blue route, which goes all the way around through a field with very little population density. It has very low risk, but is very long. So that's it's represented by this blue point in the axis of length and risk. And yeah, we want to find paths which have low enough risk, so they would be admissible by the authority, and they have good efficiency or short length, so the drone operator would be happy with the length. And essentially what we want to have are the so-called Pareto optimal paths that do the trade-off between the efficiency and the risk. And the Pareto optimal paths have smallest risk for a given length and vice versa, smallest length for a given risk. Okay, so we wouldn't want to output, I don't know, a path like this, which is more risky than, or which has the same risk as this one, but which is much longer, or no, or a path like this, which has both larger length and larger risk than this one. Okay, so we only want these so-called non-dominated paths that have the best or smallest risk for a given length and the smallest length for a given risk. So that's the general idea with trading off risk and length. And in principle, what has been done is that you can build the risk maps. So you look at every point in the domain and you think, okay, well, if this is my point where the failure happens, then how many people will be exposed? And if this distance, the lethal debris distance is d, then you essentially look at the population within radius d of this point. So here we have the population density, and then you kind of blur the density, looking at all the people which are within distance d from every pixel, and get a risk map like this. So that's a risk map for a certain value of d. Of course, there are various ways in which you can represent this risk map. You can also look at it as risk surface, but whatever. And yeah, so as you change this radius, the lethal debris distance, as it becomes smaller and smaller, less and less people are affected. And so you have the risk map more and more resembling the population density. If you only hit the people who are directly under you, then of course your risk map is the same as the population density map. Here it is. Okay, so just one slide about grids versus kind of real path planning. It's quite a standard thing to lay down a grid and try to find the paths in the grid, which in principle is okay for finding shortest paths or just for finding paths with low risk, but it's not necessarily good for the paths that care about both efficiency and the risk. So one thing is that if you use the paths in the grid, like a blue path here, it can be longer than the direct path by a factor of square root 2, about like 40%. It has many turns. It doesn't look really natural. And then there are examples. I will not go into details, but in principle, if you're trying to do a linear combination of risk and length as the weights for your paths, when you're trying to find the shortest path, a minimum cost path, or path that balances risk and efficiency, well, you may get into situations when instead of finding a short path, you find in a path which is longer and also with larger risk. Again, without going into details, one advantage of working with a grid is that these paths are easy to compute, and you don't have to use a square grid like here. You can also use hexagonal grid with more connections, like in this picture, which I took from one of the papers. But again, so you have paths that go from here to here, and at least some of them, at least the red path here, looks, well, somewhat unnatural. So why would you really follow these grid lines? You probably want to go straight. And yeah, this is what our tool does works with arbitrary density and paths with arbitrary orientations. Just a few words on how the algorithm works, some technical details. Yes, for every segment, for every potential edge in the route planning graph, we calculate how many people are affected if the drone fails along this edge. And here is a little note. It's little, but it's actually quite interesting that currently the affected area is the same as the drone's height. So if the drone flies at a certain height, then this is how far the debris can reach. I guess you might have seen it also in one of the regulations. We have, I think there is a homework problem, maybe in the practice exam, asking what do the regulations say about how far you should stay from people or which people could be affected by the failure. So there is this rule, well, it says at least 1-to-1. So like if you're flying at 100 meters, then you should think that you're affecting people within 100 meters of you or of the point on the ground beneath you. Well, the regulations say at least, and so I guess it's okay to take exactly this 1-to-1 rule and say that the little debris area is equal to the height at which the drone flies. Which, by the way, just as a tangent, this also shows a trade-off between other impacts of drone operations. So, of course, noise is one of the social concerns, and I will say a few words about social concerns in the final lecture. And the higher the drones fly, well, the less noisy they are. So on one hand, you may want the drones to fly high, but on the other hand, the higher they fly, the larger is the impact area. So you don't want the drones to fly too high. So there is a trade-off, but again, it's not immediately clear. This is nothing new in aviation in general. Again, there are quite a few different KPIs, key performance indicators, at which the aviation professionals look. And then when you speak to people and have the community involvement and other things, they weigh some of these KPIs more than others. In one example is noise. People are really concerned about noise. They want the aircraft to fly less noisy routes, but for some reason they're less concerned about emissions. Well, maybe because noise, you feel it directly, while the emissions kill you very slowly. So yeah, between the routes that have small noise and high emission and vice versa, people might want to choose one thing while actually another thing is more important. Anyway, so here again, it's just an off tangent that well, the altitude at which the drones will fly is not set yet, and there are questions of what it should be. Anyway, returning to the expected fatality rate of the path. Of course, if the path consists from several segments, then the expected fatality rate is the sum of the fatality rates on the segments. Population density should be the input. Ideally, you want to know the population, well, ideally in real time, but what we and others currently have are only the census data. And of course, these are people at homes at night, which is not exactly where people are during any kind of operations. Hopefully, we can get some kind of statistical data, since we are only estimating the expected fatality rate. Understanding where people are at different times of day is very important. How to get this data is a separate question. It's not solved yet. I've been advocating for using cameras, street cameras, and maybe even cameras in cars. Many cars have cameras now, and they may tell you how many people there are. But of course, then there are privacy issues. Of course, you can anonymize. Anyway, lots and lots of work is needed. There is a project called Testbed Kungsgatan, which a colleague of mine is running, supported by Norrköping municipality, where they installed lots of sensors on Kungsgatan for measuring the traffic of cars and also hopefully of people. And yeah, I suggested a project in one of the courses in our program to look at this data and try to understand the density of people in real time, to use it with the drone planning. But again, we are quite far from the full-blown solution on this. A lot of ideas well, being thrown out, trying to use cell phone data to understand the density of people. But the problem is that cell phone data doesn't tell you whether people are inside or outside buildings. So sheltering, understanding the sheltering is yet another question. Anyway, one way or another, you need to know the population density for the route planning. And then, yes, for every grid pixel, you know how many people there are. So for every edge going between 2 pixels, you understand the length of this edge. Well, that's simple, what the length of an edge is, but also understand how many people are affected if the drone flies this edge or another edge. And then you can use a variant of Dijkstra algorithm to compute these Pareto optimal paths. I won't go into details. It's an extension of Dijkstra algorithm. So those who took the basic logistic algorithms may learn the details, but otherwise there is some way to compute these paths. Of course, with a fine grid for the population, it's pretty hard to compute these paths. So you can look at the radius at a small radius within yourself and understand what's the best way to fly within this radius. Anyway, technical details aside, these are the outputs. So here you have this single, piece of high population density area, and you want to go between these 2 points. And there are lots and lots of paths, lots of ways in which you can go through, which trade off the length and the exposed population. And maybe there are too many even for such toy examples. So instead of looking at the full Pareto frontier of paths, so the paths that trade off risk and length, we're only looking at the lower hull of this Pareto frontier, essentially this rubber band pulled dot on the points in the Pareto frontier, and not going into too many details on how to compute them. Yes, you can get quite a few points, but not all the paths. And I'll finish with a couple of examples. So these are real examples, again, from Norrköping for different kinds of thicknesses of the path. So between these 2 points, you can go with quite a few paths, some of them going straight, some of them going fully around, and some of them kind of in between. And here are what our algorithms discover. Straight paths through the population, going like this or going around. But again, this is fully automatic. It's not that we were drawing these paths by hands. 2 more slides before I finish. All in all, what do you need to take population density into your route planning algorithms? I'm using the slide back from 2017, done by Maitre at a conference. So you want to understand which variables influence the risk, and then you want to incorporate the population density into your planning, and finally you want to do the real time thing. And well, this is what our GUI does. You can look at the length of the path and how it goes and understand what the risk is. You can also do algorithmically find different paths, and hopefully in the future we will also get some kind of real-time data on where the population is one way or another and incorporate it into the planning. A lot remains for future research, but at this point, let me stop here.